Hi, I'm Brad Potteiger, and today I'm going to present my paper on the security in mixed time and event-triggered cyber-physical systems using moving target defense. I'd first like to thank my co-authors, Feiyang Ke, Abhishek Dubey, Zhang, and Zenifan Koutsoukos at Vanderbilt. Even though this work was done for my PhD at Vanderbilt, I'm happy to say that I've since graduated and am now a senior researcher at the Johns Hopkins University Applied Physics Lab. Software is vulnerable. Cyber-physical systems, or CPS, are especially vulnerable due to the significant amount of legacy software that they contain. Due to the tightly coupled nature between the cyber and physical environments, it's not only important to maintain integrity, but equally as important to maintain safe operation and availability under a cyber attack. Automotive applications are complex systems of systems with millions of lines of code, dozens of ECUs, and a ton of legacy vulnerabilities. Further, due to the similarity of software, if you can exploit one car, you can compromise thousands of vehicles of the same model around the world. To mitigate against generic exploits and legacy software vulnerabilities, my research has focused on leveraging moving target defenses to limit the impact of attacker reconnaissance in finding and exploiting vulnerabilities. Specifically, I focused on using event-triggered implementations of instruction set randomization or encoding instructions at the binary level, address-based randomization, or shuffling a program at function granularity, and data space randomization, where you can encode local variables on the stack. The reality is, most CPS use time-triggered architectures due to the need to guarantee predictability and reliability for safety purposes. However, cyber attacks are unpredictable and can happen at any point in time. It's not optimal to wait until the next period to react to an attack. Detection and reconfiguration must be fast enough to maintain stability of the controller. Our hypothesis is that by combining event and time-triggered functionality into a hybrid architecture, we can leverage the benefits of both, providing predictable behavior under normal circumstances, while being flexible enough to detect and recover rapidly from a cyber attack. Furthermore, by combining ISR, ASR, and DSR, we can provide a comprehensive and proactive defense against memory corruption vulnerabilities within legacy software. The system model of our paper revolves around an autonomous vehicle with an ECU cluster, communication bus, and CPS controller with embedded code. The ECU cluster provides the capability to sense the physical environment and control the actuation of the car, while the CPS controller contains the underlying logic to compute the respective output actuation commands. To support time-triggered functionality, we leverage the ARINC 653 standard to provide for predictable behavior of the underlying processes. As seen in the left figure, ARINC 653 contains two components, partitions and processes, which we will refer to throughout the presentation. Partitions are isolated and protected memory regions that are strictly protected in time. A partition can contain one or multiple processes which represent the underlying tasks that are executed. Additionally, communication can occur through inter-partition and intra-partition methods, and a hyperperiod represents the time allotment for a series of repeatable consecutive partitions. Our threat model includes a more detailed model, including a sensor cluster reporting images and speed, actuation cluster controlling steering, throttle, and braking, a CPS controller with the underlying logic, remote function actuator, which is pretty much like a key fob, and telematics control unit, which serves as an intermediary for relaying diagnostic messages to remote operating stations. It's important to note that in our threat model, the CPS controller is assumed to be the only vulnerable component containing a memory corruption vulnerability, such as a buffer overflow. By using the TCU as an entrance, attackers can remotely inject malicious payloads into the network to exploit this vulnerability within the CPS controller. Furthermore, because of the one-way inter-partition communication of ARINC 653, the CPS controller cannot compromise any previous components such as the sensors and perception processes. This means that we also assume that our underlying architecture is secure as well. Looking at the same figure, our process contains 4 steps: sensor processing, perception, control computation, and actuation. These 4 processes correspond to the 4 partitions within our ARINC 653 architecture. Additionally, the module manager serves as the parent process to oversee and respond to suspicious events within the underlying partitions. Because of the CPS controller is vulnerable component, we first leverage a simplex-like architecture to break the main process into 2, a default high-performance controller and a fail-safe controller with less performance but security guarantees. Additionally, we wrap each controller process within a security sandbox referred to as a DBT or dynamic binary translator. The DBT provides the underlying MTD defense implementations to create a secure runtime for each vulnerable process, including the default and fail-safe controllers in our scenarios. In terms of process flow, our architecture contains 3 stages: design time, where we do static analysis; runtime, where we perform moving target defense randomization; and control reconfiguration, where we provide capabilities for safe and reliable detection and recovery. Design time starts with a binary executable in which we lift to an LLVM IR representation to perform points to analysis. Looking at the example, you can see that the output of the points to analysis process is in the format of individual graphs. Each graph corresponds to a single variable relationship, identifying the respective load and store assembly instructions and utilize memory locations. By identifying the variable and memory relationships, we can assign unique randomization keys for our DSR implementation. At load time, our DBT first encodes instructions at the binary level while shuffling program memory at function granularity. Then at runtime, a normal instruction pipeline is utilized. Once an instruction is fetched, it's first decoded and assessed for type. Under default circumstances, the instruction is executed as normal. Code injection attacks will result in invalid instruction exceptions due to ISR, and code reuse attacks will result in invalid memory access exceptions due to ASR. If it's a stored instruction, the respective variables will be stored in memory as redundant copies encoded with 2 different randomization keys. When a load instruction is found for that specific memory location, each variable copy is retrieved, de-randomized, and compared for equality. If they're different, then data tampering is detected and an attack is triggered. Once an attack is detected, a POSIX signal is sent to the module manager, which identifies the compromised partition, spawns, and then executes the backup controller. As mentioned before, an attack can occur at any point in time, whether the beginning or end of a period. At the worst, our approach successfully recovers while missing only one deadline. In this case, we reuse the last actuation command to maintain control stability. To evaluate our approach, we developed a hardware-in-the-loop testbed using embedded hardware consistent with an automotive deployment environment. For time-triggered functionality, we leverage open source ARINC 653 middleware while relying on Mambo for our MTD dynamic binary translator and Carla to simulate the physical autonomous vehicle dynamics. Our evaluation revolves around an advanced emergency braking system case study, in which an autonomous vehicle has to stop before colliding with a leading car parked at a traffic light. Looking at the bottom figure, the module manager is implemented with 300 lines of C++ code leveraging ARINC 653 health monitoring APIs, while the hyperperiod of the partitions is around 100 milliseconds. The default CPS controller is a 3-layer sequential neural network, and the fail-safe controller brakes as hard as possible to avoid crashing into the leading car parked at the traffic light. Our evaluation leverages 3 scenarios. The first scenario involves a code injection attack, which injects a malicious payload to exploit the buffer overflow within the CPS controller through the telematics control unit. After this, the payload is directly executed to max out acceleration to crash into the leading car at maximum speed. Under normal circumstances, you can see that the attacker was successful in causing the crash with the velocity greatly increasing and the distance dropping to 0. However, with MTD enabled, the attack fails, and while execution is successfully transitioned to the failsafe controller, collision is avoided. You can see that the distance levels off and the velocity decreases to 0, well before the 0 mark where the car would crash into the previous car. The second scenario involves a code reuse attack, which instead of directly executing code, redirects control flow to reuse existing code within the steering function of the CPS controller. When successful in the baseline case, the attacker is able to successfully cause the car to turn left off of the road. However, when MTD is enabled, the attack fails and the failsafe controller is able to keep the car driving straight and on the road while stopping in time before crashing into the parked car. The final scenario involves a non-controlled data attack. Instead of redirecting control flow, the attacker tries to override adjacent variables on the stack to indirectly affect controller output. In this case, the attacker successfully overwrites the distance variable to trick the car into thinking it is further away than it actually is, thus causing a crash. However, when MTD is enabled, data tampering is detected and the fail-safe controller takes over, maintaining safe braking of the vehicle to avoid the crash. To analyze performance, we conducted 1,000 experiments under varying conditions. By looking at the left figure, you can see that the respective overhead varies depending on the combination of security protections. As such, slack time will be the primary influencer in what types of protections are acceptable within an application. Additionally, from the right figure, you can see the starting the backup process takes up the majority of the recovery time. To reduce recovery time, designers can actually instead choose to have the backup process remain idle, taking up more memory, but reducing the time to recovery. In conclusion, we have provided a proactive, comprehensive solution leveraging moving target defenses while developing a hybrid time and event triggered approach to provide predictability while rapidly detecting and reconfiguring during an attack. Additionally, we have developed and customized a hardware-in-loop testbed to evaluate our approach on embedded hardware consistent with automotive deployment environments. For this paper, we focus on the automotive domain, but in the future, this technology can also be applied to other applications as well, such as defense, railway, medical devices, and SCADA systems alike. I'd like to again thank ISORC for the opportunity to present this work, and we'll now open up to any questions that you guys have.